We will now move from the paper and board sector to a set of high temperature process in other energy intensive industries. And for that, we have MetaWave coordinator, María Herrando, that is a senior researcher at ITA, the Aragon Institute of Technology. María, the floor is yours.
Good morning, everyone. So I'll explain MetaWave project. So here, similar as with steam dry, what we plan to do is to target high energy demand industries that strongly rely on fossil fuels and therefore have a big amount of greenhouse gas emissions. Our solution proposes the introduction of advanced microwave heating systems that replace high temperature heating processes, meaning more than 400 degrees in the conventionally operation. So what we plan is to demonstrate these technologies in 3 distinct sectors, as Elena mentioned before, that will improve energy efficiency, faster processing, and also better controllability. The sectors, as you mentioned, are the ceramic sector, the asphalt, and the aluminium, and I will enter a bit more into details later on. So the overall objectives is to develop new design methods and consolidate process for the introduction of microwave technologies as a replacement for fossil fuel heating systems. Thanks to this, we expect to use recycled materials for refractories, as well as more than 5 new additives investigated, leading to an energy reduction of more than 30%. We also plan to optimize the industrial heating process and reduce the energy demand by integrating different digital technologies. This way, we will achieve a process manufacturing efficiency improvement by 30%, as well as a decrease in the process energy consumption by more than 5%. Next objective is to fully capture the potential of renewable energy integration and energy flexibility through an operation of the decision support tool that would lead to a cost reduction by more than 5%, as well as an CO2 emissions reduction by 20 to 25%. The next one is to deploy and validate an integrated system, combining high energy efficiency breakthroughs and target increased productivity. For this, we plan to increase productivity by 3 to 10%, as well as 10% weight reduction, and also to improve the absorbed per unit volume, power absorbed per unit volume between 25 to 30%. The fifth is to ensure the techno-economic feasibility of these systems and pave the way towards the technological adoption and acceptance and upscaling. For this, we are developing for each use case techno-economic assessments, life cycle assessment, a financing roadmap to TRL9, as well as replication and transferability roadmaps to at least 3 different industries. And finally, to convincingly demonstrate these technologies in 3 demonstrators I was mentioning. So the project is 9.5 million euros. It started in January 2024 and will finish at the end of next year. So it's 4 years project. We're 20 partners from 9 different countries. So we not only tackle, let's say, the prototypes, but also address different key innovation technologies, including improvement in energy efficiency, as I was mentioning, by improving the applicator design, improving insulation, and therefore reducing thermal losses. We also expect to reduce CO2 emissions and also improve heat recovery, therefore reducing the environmental impact. We are also introducing new circular materials by new refractories and subsectors from recycled waste. We aim to improve the operational economics by the development of a virtual power plant, then selects and improves flexibility and integration with renewable energies. And we are also tackling safety and standards as we are using microwave technologies. So as you can see, the result is not only a single machine, but an integrated industrial solution. Now I will explain each of the use cases, trying to explain different things that Elena mentioned. So the first one is the porcelain tiles firing within the ceramic production. We have here Gres de Aragon, that is from Sanca Group in Spain. So right now the process, as you can see there in that image, the industrial one is a continuous process of 1000 to 1300 degrees that uses torches of natural gas, and we plan to replace those torches by microwave-based plasma. So here the key challenge is this high temperature processing and the low loss material that undergoes all those phase changes. So we have to avoid the cracks that might produce with the heating. What we did here is to develop a CFD model to support the design of the new system. We had the curve that the firing curve that has to be followed, and we trying to reproduce it. We already have the final prototype, and now they are in the assembling process. For the second use case, it's the aggregate heating within the asphalt production. We also have a Spanish company, Ecopa. So here the process right now is continuous. It's a process temperature with a flame that uses low sulfur heating oil at 1,400 degrees. They are going to quickly dry and heat the aggregates. Is that trommel that you can see there in the picture. And we plan to replace it by direct microwave heating with a hot air flux that removes the moisture. So considerably reducing the temperature down to around 200 degrees process temperature. Here the challenge is the volumetric heating and the selectivity of microwaves, as well with integration and coupling with this hot air. And for this, we developed a couple electromagnetic finite elements and CFD model. And now the prototype is already actually built and assembled. And now they are finalizing the last fat test, and then they will be shipping in the next week to start with the demonstration at the pilot site, at the demo site. The last one is in the anode baking in the aluminum production. Here we have grease from grease Medlen. It's a current process, is a batch process of 1,000 degrees that uses natural gas and hydrocarbon. We plan to substitute by that microwave and induction. Here, as and I was mentioning, we have the challenge of the high electrical conductivity material generated due to this preliminary dielectric heating phase, and also the large dimensions of the load, as you can see there, an anode. And we developed an electromagnetic and thermal simulation for the design. The prototype is already on-site operating. So the main technical, economic, and regulatory barriers, we have data and cybersecurity due to the data sharing hesitation and ownership concerns, so which we plan to overcome with secure data infrastructure, real-time processing. Second one is the techno-economic uncertainty due to the lack of reliable cost and performance data. For this, we are developing techno-economic and life cycle assessments. The third one is the skills and safety due to the limited expertise, safety concerns, and low digitalization, which we plan to overcome with training, safety design, and guidelines. Then we also have high investment costs due to the high capex, especially for SMEs, which we plan to overcome with green finance access and also optimization tools. And the last one is the grid and electrification. So we might have an increased load that might rely on fossil-based power systems, which we plan to overcome with the development of the virtual power plant energy management system for the renewable integration and flexibility. So as we know, the scaling requires more than replacing equipment. So it's not only the prototype, but also, as you can see, we have to tackle 4 main items. We have integration with heat recovery and insulation and hybridization. We have the control, so we're developing new sensors, digital intuition, reduce order models that will help maintain the quality in these harsh environments that I was mentioning. Flexibility, for this, we have this virtual power plant to align production with the renewable availability and also the market energy prices. And the trust. So we have safety standards and economic evidence that are essential for the adoption. So we have all of this industrial approach to tackle. Our scale-up roadmap includes, at the end of the project, we expect to achieve TRL6 with the validation in real industrial conditions. Then 2 years later, it's the upscaling with a modular scale-up. So we develop the prototypes in a modular way so they can be easily scaled up. And cross-sector expansion. 1 year later, the pre-market with the early adopters and in-field validation and a commercial version of the systems. 1 year later, market rollout within the 3 sectors with some strategic partnerships. And finally, the expansion to international markets and technology transfer. And I believe this is all from my side. Thank you.
Thank you, Maria.